Hi students, today I wish to take a revision class on moving charges and magnetism for the students those who are writing NEET examination. This revision class completes in 3 sessions and this is the first session of the class. This session includes magnetic Lorentz force, motion of the charged particles in uniform magnetic field and motion of the charged particles in both electric and magnetic field and also cyclotron. Now let us start the class. The first point, magnetic Lorentz force. Magnetic Lorentz force is the force acting on a charged particle when it is moving through a magnetic field. Okay, now what is the equation to find magnetic Lorentz force? Let Q is the charge moving with velocity v through a magnetic field of strength B by making an angle theta. Then the magnetic Lorentz force is given by Fm vector is equal to Q into V vector cross B vector. Its magnitude can be written Fm is equal to Q V B sin theta, where theta is the angle between the velocity vector and magnetic field vector. Okay, now we can expect some questions related with the magnetic Lorentz force. The first one is when this force becomes zero. We can say the magnetic Lorentz force Fm equal to 0 first point, when the charge of the particle is 0, that is the particle is a neutral one. Okay, that is Q equal to 0. Second case, when the velocity of the particle is 0, that is when the charged particle is at rest, that is V equal to 0. Third point, when sin theta equal to 0. Sin theta equal to 0 means theta is equal to 0 degree or 180 degree. That is when the charged particles are moving parallel or anti-parallel to the magnetic field. So the next point is, or the next question is, when this magnetic Lorentz force becomes maximum. So we can say magnetic Lorentz force becomes maximum when sin theta equal to 1. That is sin theta equal to 1. That is theta equal to 90 degree. It means when the charged particle is moving perpendicular to the magnetic field. That is V vector is perpendicular to B vector. Okay, next question is about the direction of magnetic Lorentz force. So the direction of magnetic Lorentz force. We have the equation for magnetic Lorentz force in vector form as Fm is equal to Q into V cross B. So we can say the direction of magnetic Lorentz force is perpendicular to the plane containing V vector and B vector. So that is the direction. So direction of magnetic Lorentz force is perpendicular to the plane containing V vector and B vector. Okay, what is the meaning of this statement, or what is the meaning? From here, from this idea, we can say magnetic Lorentz force is perpendicular to the velocity vector. and also Fm is perpendicular to B vector. Okay, from the same idea we can expect a question, what is Fm vector dot V vector? Since these two vectors are perpendicular, this is equal to 0. Dot product between perpendicular vector is equal to 0. Similarly, you can say what is Fm vector dot B vector, that is also equal to 0. Then again, Fm dot V equal to 0, then you can say what is Fm dot S vector. Fm dot S. Fm and V are perpendicular, so what also perpendicular? Fm and S are also perpendicular, so we can take this is also equal to 0. What is the meaning of Fm dot S? Force dot displacement vector, that gives the work done. So we can say that work done is equal to 0, that is work done by magnetic Lorentz force on the charged particle moving through magnetic field is 0. That's a very important point. And again, we know that according to work energy theorem, this work done is equal to change in kinetic energy. So we can write from here change in kinetic energy equal to 0. Okay, what is the meaning change in kinetic energy is 0? That is kinetic energy is constant. So you can say kinetic energy of the particle is constant. Kinetic energy constant means kinetic energy is equal to half mv square, where v square means speed square. So speed is constant. So you can say that here the speed of the charged particle is constant. Then what about velocity of the charged particle when it is moving through magnetic field? We can say that velocity may vary, because velocity is a vector quantity, so it can vary. Okay. And what about momentum? Momentum is also a vector quantity that can vary, maybe constant or a variable. Okay, but you can say kinetic energy and speed is constant when the charged particle is moving through a magnetic field. So these are very important points. Okay, and we got the direction of magnetic Lorentz force also. It is perpendicular to the plane containing V vector and B vector. But there is a problem. How can you find the exact direction of magnetic Lorentz force? Let me explain that with an example. Okay, we can find the direction of magnetic Lorentz force by using the equation Fm is equal to Q into V cross B. This is one of the method. Okay, for example, you are given a positive charged particle is moving along positive x direction to a region where magnetic field is acting along positive y direction. Then what is the direction of magnetic Lorentz force? Okay, we can find the direction by using this equation. Take this equation, Fm is equal to, what is Q here? Positive charge, so it is plus Q. Remember, you have to take the sign also while calculating the direction into V, velocity is along x direction, cross magnetic field along y direction. What is I cross j? I cross j is k. So we can say Fm vector is equal to Q V B K cap. So this is the equation, or this is the answer. So we can say that magnetic Lorentz force is along positive z direction. Okay, one more example. You consider a charge is equal to minus q, that is a negatively charged particle is moving along z direction and magnetic field is acting along y direction. What is the direction of magnetic Lorentz force? The same equation we can use. Fm vector is equal to q into, but here q is minus q, negative charge, so minus q into v cross b, v k cap cross d j cap. So here what is k cross j? J cross k is equal to I, k cross j is minus I, so the answer is minus q into vb into minus I cap, minus into minus plus, so the answer is qvb I cap. So what is the direction here? Positive x direction. This is the one method to find the direction of magnetic Lorentz force. Remember, while you are calculating, put the sign of the charge. Okay, and here one more idea. If the charge is positive, magnetic Lorentz force is parallel to v cross b. Is it correct? What is v cross b? Z xy, I cap cross j cap is z. Then what is the direction of magnetic Lorentz force? Z direction. The meaning, if the charge is positive, magnetic Lorentz force is parallel to v cross b. Okay, and if the charge is negative, what is the meaning? What is the case? The magnetic Lorentz force is anti-parallel to v cross b, just opposite to the direction of v cross b. So that is the method to find the direction of magnetic Lorentz force. Okay, and there is one more method to find the magnetic Lorentz force, and the rule, and there is a rule, and the rule is Fleming's left hand rule. Now we can move to that point. What is Fleming's left hand rule? Fleming's left hand rule, FLHR, Fleming's left hand rule. This rule states that stretch the three fingers of our left hand in mutually perpendicular direction. This rule says that stretch the three fingers of our left hand in mutually perpendicular direction. The fingers are forefinger, central finger and thumb. Remember, forefinger should be in the direction of magnetic field, central finger should be in the direction of current. Then the thumb will give the direction of magnetic Lorentz force. That rule is called Fleming's left hand rule. Now the question is, how can we apply this rule? Let me explain. Let us consider the case a negative charge minus q is moving downward through a region where the magnetic field is acting along this direction. What is the direction of magnetic Lorentz force? Okay, we can find the direction using Fleming's left hand rule. Stretch the three fingers of our left hand in like this. Forefinger is in the direction of magnetic field, so here the direction of magnetic field like this. Central finger is in the direction of current, not in the direction of motion of the charge. Here the negative charge is moving in downward direction. Then what is the direction of current? We know that the direction of current is along the direction of positive charge or opposite to the direction of negative charge. Since the negative charge is moving in downward direction, we can say the direction of current is upward. So here the current is in this direction, so central finger is moving up. Then what is the direction of the magnetic Lorentz force? Inward. So you can say that the direction of magnetic Lorentz force is perpendicular and in. Okay. Like this you can find the direction of magnetic Lorentz force by using Fleming's left hand rule. I think all of you got the idea how to find the direction of magnetic Lorentz force. You can expect this question. Okay, these are the main points about magnetic Lorentz force. Once again, the force can be calculated by the equation Fm vector is equal to Q into V cross B. Its magnitude is QVB sin theta, and it becomes 0 when the charged particle is moving parallel or anti-parallel. The force is maximum when the charged particle is moving perpendicular, and the maximum value of magnetic Lorentz force is QVB. Okay, then the direction of magnetic Lorentz force. Okay, and here the important point is this: magnetic Lorentz force is acting only on the charged particle when it is crossing the magnetic field. When it is crossing the magnetic field. Okay, so these are the points. Now we can move to the next point of the chapter. Next point is Lorentz force. Lorentz force means it is the net force acting on the charged particle when it is moving through a region containing both electric and magnetic field. Okay, so it is the net force when it is moving through electric field and magnetic field. Means on the charge there are two forces acting. One is the electrostatic force Fe and the other one is the magnetic force Fm. That is called the magnetic Lorentz force. Okay, and we already studied the electrostatic force acting on the charged particle is given by QE, and the magnetic Lorentz force is given by Q into V cross B. So the equation for Lorentz force is F vector is equal to Q into vector E plus V cross B. So this is the equation for Lorentz force. Okay, and this equation is used when the charged particle is moving through the region containing both electric and magnetic field. Okay, next is the motion of the charged particle through uniform magnetic field. Here, the first point you have to remember is this one. If you are given a question related with the motion of a charged particle in magnetic field, then you can solve that question by finding the magnetic Lorentz force, because the force acting on the charged particle moving through magnetic field is the magnetic Lorentz force. Okay, so that is the idea to solve the problems related with the motion of the charged particle through magnetic field. Okay, and here I am explaining this thing in three cases. The first case is the motion of the charged particle through a magnetic field parallel or anti-parallel to the field. Second one is charge is moving perpendicular to the field, and third one is charge is entering the field by making an arbitrary angle theta. Okay, in all these cases we are solving the problem by finding the magnetic Lorentz force. Okay, let me start the first case. Here the charged particle is moving parallel or anti-parallel to the magnetic field. Here two figures are given. In the first figure the charged particle is moving parallel to the magnetic field, and in the second figure the charged particle is moving anti-parallel to the magnetic field. And this is uniform magnetic field in the plane of the paper. Okay, and in this case the angle theta is equal to 0 degree. In this case the angle theta equal to 180 degree. I already explained that this type of problems can be solved by finding the magnetic Lorentz force, because only the force acting is the magnetic Lorentz force. So we have the equation for magnetic Lorentz force as Fm is equal to QVB sine theta. When the charged particle is moving parallel, the angle is 0 degree, and when it is moving anti-parallel, the angle is 180 degree. So in both cases, what is the value of the magnetic Lorentz force acting? 0. So this is the first question. What is the magnetic Lorentz force is acting when the charged particle is moving parallel or anti-parallel? That we already studied. That is equal to 0. Then, what is the acceleration of the charged particle in this case? You can say acceleration is given by force by mass, and here the force is 0, so the acceleration is equal to 0. Okay, the next question, what about the velocity of the charged particle? Since the acceleration of the particle is 0, we can say that there is no change in velocity, so the velocity is a constant. So in this case, velocity is a constant. And velocity constant means, what about the speed? Speed is the magnitude of velocity, that is also a constant. If speed is constant, what about kinetic energy? Kinetic energy is also constant. What about the momentum of the charged particle? Velocity is constant, therefore momentum of the charged particle is also constant. You got it? Now the question is, what type of motion is for the particle? What type of motion execute the particle in this case? So we can say that velocity is constant, that means the charged particle is moving along a straight line with constant speed. That is, the charged particle is moving along a straight line, so the path is a straight line. And what is the motion? It is a uniform straight line motion. So we could conclude the motion of the charged particle as uniform straight line motion. So these are the important points, and each points are a question. You can expect each points as questions in your NEET examination. Okay. Next point, moving charged particle moving perpendicular to the magnetic field. Here I am given. Here you can see two figures. One is the magnetic field represented by dots, means uniform magnetic field perpendicular and outward. And the other one is represented by cross mark, that is also a uniform magnetic field but perpendicular and inward. Okay, now you consider a particle, a charged particle Q, moving through this magnetic field like this. Expect this is a positively charged particle. Okay, you can expect so many questions. First point, you can say here the charged particle is moving perpendicular to the field, because field is perpendicular and outward. So the angle between the velocity vector and magnetic field vector is 90 degrees. So you can say that here the angle theta is equal to 90 degree. Therefore, there is a force called magnetic Lorentz force given by Fm is equal to QVB sine theta. Since sine theta 90 equal to 1, sine 90 equal to 1, it is equal to QVB. So this is the value of the force on the particle. First question. Second one, what is the acceleration of the particle? We know the acceleration is given by force by mass. Here the force is qvb, so the acceleration of the particle is qvb divided by m. Okay, from here you can say that velocity goes on changing, so the velocity is a variable. It is not a constant, it is a variable. So what also? Momentum also a variable. So velocity is variable and also momentum a variable. Okay, velocity variable means what about the speed of the particle? And what about the kinetic energy of the particle here? So here the important point is this magnetic Lorentz force is perpendicular to what vector? Velocity vector that we already studied. So magnetic Lorentz force is perpendicular to velocity vector. You can say the first point is the speed of the particle is constant. So we can say what about kinetic energy? Kinetic energy is also a constant. Okay. So we can say that when the charged particle is moving perpendicular to the magnetic field, it experiences force, acceleration is there, velocity and momentum are variable, speed and kinetic energy are constant because the magnetic Lorentz force is perpendicular to the velocity vector. But again, very important point is what type of path the charged particle follow. Okay, in the last session we studied that the charged particles is moving along a straight line when it is passing through a magnetic field parallel to the field. But here what is the case? So here force is perpendicular to the velocity vector. So we know that the charged particle will move along a curved path. So the path is a circular path. So a charged particle describes a circular motion. What type of circular motion? Is it uniform or non-uniform circular motion? That is a question. We know that speed is constant. So when a body is moving along a circular path with constant speed, means that is a uniform circular motion. So in this case, you can say the charged particle describes uniform circular motion, and this circular motion is called cyclotron motion. Cyclotron motion. That is uniform circular motion of a charged particle in a perpendicular magnetic field is known as cyclotron motion. Okay. Next you can expect a question that in which direction it moves. We know that it describes a circular motion. Is it a clockwise circular path or anti-clockwise circular path? How can you find that? For that, you find the direction of magnetic Lorentz force. Okay, I am applying Fleming's left-hand rule. Here this is the direction of magnetic field, this is the direction of current. So what is the direction of current? This is a positive charge moving in this direction. So what is the direction of current? So direction of current is also in this direction. Now we can apply. So magnetic field perpendicular and outward, the direction of current in this direction. So what is the force? Downward direction. So you can say the force is acting perpendicular and downward. So this is the magnetic Lorentz force. Then what happens? The charged particle will deflect in downward direction like this and describe a circular path like this. So this is the circular path. So clockwise circular path, and force is acting towards the center of this circular path. So you can say that here magnetic Lorentz force is acting as centripetal force, because the force acting towards the center is called centripetal force. So here the required centripetal force is provided by magnetic Lorentz force. Okay, so here I explained 2 points. One, how can you find the sense of motion of the particle? Is it a clockwise circular path or anti-clockwise? Okay, I think you understood how to solve this question. And the second point is, here the required centripetal force is provided by magnetic Lorentz force. Okay, now another question is this one: in which plane this circular motion executed? What is the plane of this circular motion? We know that here the magnetic field is perpendicular and the circular path is in this plane. So we can say that the circular motion takes place in a plane perpendicular to the direction of magnetic field. So that's a very important point. What is that? The circular motion takes place in the plane perpendicular to the direction of magnetic field. Okay. Again, you can expect, what is the radius of this circular path? What is the time period? What is the time period of the circular motion? What is the time period of this circular motion? What is the frequency? What is the angular frequency? Like that questions you can expect, but here I am not deriving that equations. I am directly giving the equations. First point is this one: centripetal force is provided by the magnetic Lorentz force. This is the basic idea. From this you can find all the things: radius, frequency, time period, etc., etc. All are calculated from this equation. Okay, you just substitute the centripetal force is equal to mv square by r and magnetic Lorentz force in this case is equal to qvb, and solve this equation. You get all the points. First equation you need is r is equal to mv divided by qb. What is m into v? Is equal to momentum, that is equal to p pi qb. And what is the momentum in terms of kinetic energy? If you are given the kinetic energy of the particle, we know that momentum is equal to root of 2mk, where k is the kinetic energy divided by qb. Okay, one more question. If the charged particle is initially moving through an accelerating potential, then what is the equation for radius? We know that when the charged particle is accelerated through a potential v, then kinetic energy is given by q into v. Q is the charge, v is the accelerating potential. So you can substitute q into v here, and solving we get another equation for radius, that is equal to 1 by b into root of 2m capital V divided by q. Here this capital V is called accelerating potential. So this is actually accelerating potential. Okay, so this is very important. You got the idea? Okay. Now what is the time period of this circular motion? Time period is given by distance divided by speed. Distance in the case of circular motion, uniform circular motion, is 2 pi r divided by v. Here r equal to, already we got r equal to mv by qb, v cancelled, so the time period is 2 pi m divided by qb. So this is the equation for time period of circular motion. And what is the frequency of circular motion? And that frequency is called cyclotron frequency. What is the cyclotron frequency? Nu is equal to reciprocal of time period, that is equal to qb divided by 2 pi m. This is the question. Okay, so this is the frequency. And here the important point is, in this equation and in this equation, you can see the time period and frequency depends on the magnitude of the charge, magnetic field and mass of the charge. But it is independent of, so you can say that both the time period and frequency. And also one more point you can say, that is called angular velocity. Angular velocity is equal to 2 pi nu. That is equal to 2 pi cancel. It is equal to q by m. This is called angular frequency. That is all these three, time period, frequency and angular frequency, are independent of what is not coming in this equation. R is not coming. The radius is not coming. And also the speed of the particle. So you can say it is independent of radius of the circular path and speed of the particle. Okay, next question is, if you are given that a charge is entering the magnetic field and moving like this. Okay, what is the charge of the particle? Is it a neutral particle, positive charge or negative charge? That is the question. Okay, the first question is this one. If the charge and a magnetic field are given, how can you find the sense of revolution of the particle? But here the sense of deflection, or here the direction of deflection is given. What is the charge? First point, it is not neutral, because if it is a neutral particle, it does not deflect, because there is no magnetic Lorentz force on the particle. So it is not a neutral particle, so it is a charged particle. Is it positive or negative? That is the question. Then how can you find? Only the thing we know, the direction of magnetic field is perpendicular and inward. Anything else? Yes, one more thing. It is deflected upward means there is a force in which direction? In upward direction. So here we can expect a force like this, and that force is magnetic Lorentz force. So now you know the two things. One is the direction of magnetic field and the other one is the direction of magnetic Lorentz force. Now you can apply what? Fleming's left hand rule. This is the direction of magnetic field. What is the direction of magnetic field? Direction of magnetic field is perpendicular and inward like this. And this one is the force. What is the direction of force? Upward. So the force is upward direction. So what is this one? This is the direction of current. So you got the direction of current. So what is the direction of current here? This is the direction of current. Okay. Now we can say what is the direction of motion of the charged particle like this. What is the current like this? Both are in the same direction. If the current and the charge are in the same direction, then the charge is positive. So you can say that it is a positively charged particle. You got it? If the direction of current is in the opposite direction, we can say that what? The direction of the charge and direction of current are opposite. Direction of motion of the charge and direction of current are opposite. So what is the charge? It is negative charge, because the current is always opposite to the direction of negative charge. Opposite to the motion of the negative charge. Okay, all of you got the idea. So you can expect all these questions in the examination, so study it. Okay, remember the points. Okay, so the third case, charged particle moving at an angle theta with the magnetic field. Here a charge Q is moving with a velocity v through a magnetic field B by making an arbitrary angle theta. Okay, then how can you solve the question? We know that velocity is a vector quantity, so we can resolve it to two. One is velocity component parallel to the magnetic field. That component is given by v cos theta. Second component is along this direction we can take it as V perpendicular component. V perpendicular means it is perpendicular to the magnetic field. So that is equal to V sine theta. So we have two component of velocities. Since this velocity is parallel to the magnetic field, so there is no force due to this component. But this component is perpendicular to the magnetic field, so there is a maximum magnetic Lorentz force. You got it? So the charged particle moving in the direction of magnetic field is along a straight line motion. Sorry. So the charged particles moves along a straight line with the constant velocity because of this component, and the charged particle describe a circular path because of this component of velocity. So the exact motion of the charged particle is the combination of straight line motion and a circular motion, and it is like this. So this is the motion of the charged particle, and this is called helical path, that is helical motion. So the first point is this one. What type of motion the charged particle execute in this case? So you can say it is a helical motion. Okay, you can expect another question. What is the pitch of the helical path? Pitch of the helical path. Pitch means the horizontal distance traveled during one circular motion, and that is given by the equation. Since it is moving along horizontal direction, horizontal distance you want to find, so it is velocity into time, because it is a uniform motion. So velocity parallel, and the time taken is the time for one circular motion, so that is capital T. So this is equal to 2 pi m divided by QB into V parallel. V parallel is what? V cos theta. So it is equal to 2 pi m V cos theta divided by QB. So this is the equation for pitch of the helical path. Remember, you have to substitute the velocity parallel to the magnetic field. The third point is, what is the radius of this motion? Radius of this motion is given by R equal to mv by qb. Which velocity component you have to substitute? We know that circular motion is due to the vertical component of velocity, so you have to substitute here v perpendicular. So this is mv sine theta divided by qb. So the motion is helical motion, pitch of the path is like this, and radius is given by this equation. And another question is, what is the axis of this helical path? So this is the helical path, and the axis of helical path is this one. So you can say the next point as the magnetic field is acting as the helical, So the fourth point, the axis of the helical path is the magnetic field. So these are the points about the motion of the charged particle by making an angle theta with the magnetic field. Okay. Next point is cyclotron. Cyclotron is a device used to accelerate positively charged particles to very high energy. Okay, it was first developed by Lorentz and Livingston. What is the principle of cyclotron? By using cyclotron, you can accelerate the charge to very high energy. How it is possible? It is possible by using two fields. One is electric field and other one is magnetic field. You pass the charged particle through moderately high electric field a number of times with the help of a perpendicular magnetic field. Then you can accelerate the charged particle to very high energy. Now let us discuss the construction of cyclotron. The main parts of the cyclotron is D1 and D2 called Ds. These are two semi-cylindrical metallic chambers and they are separated by a very small distance and there is a small gap between the Ds. And the Ds are connected to a high frequency oscillator to provide high potential difference between the Ds. And these Ds are placed in a magnetic field. That magnetic field is acting perpendicular to the plane of the Ds, like this. This is the magnetic field and the magnetic field is acting perpendicular to the plane of the Ds. Okay, these are the main parts of a cyclotron. Now how it is working? The charge to be accelerated is at the center. Okay, let us initially consider the D2 is at a positive potential and D1 is at a negative potential. This potential difference is provided by using high frequency oscillator. So this positively charged particle, okay, here we are accelerating this positively charged particle. So this positively charged particle will attract towards the negatively charged Ds and enter into the Ds. After entering to the Ds, electric field inside the Ds are zero because of the electrostatic shielding effect. So what is only there? A perpendicular magnetic field. So it will describe a circular path and after completing a semi-circular path, it reached the gap again. At the same time, you reverse the potential. Now D2 is at negative potential and D1 is at positive potential. Then the charged particle will accelerate into D2 and it will enter inside the D2 with a higher velocity. From here to here or inside the Ds, there is no change in speed, but there is a change in velocity due to the change in direction. And the velocity increases only in between the gap because of the presence of electric field. So electric field helps to increase the speed of the charged particle and magnetic field helps to pass the charged particles number of times through this moderate electric field. So it will again describe a semicircular path and reaches the gap again. Okay, and this process continues. So the charged particle will describe a spiral path, that is circular path of increasing radius, and it gets its maximum energy or highest energy when it reaches the periphery of the Ds. In this way you can accelerate the charged particle. Okay, so that's very important, and this process fulfilled only when the frequency of cyclotron motion and the frequency of high oscillator are same. There should be a resonance. When the resonance lows, the charged particle gets out of resonance, so further acceleration is not possible. Okay. We know that here the particle is moving along a circular path because of what? The magnetic Lorentz force. So the magnetic Lorentz force is acting as the centripetal force. On solving you will get the equation for radius, equation for time period, equation for frequency called the cyclotron frequency, and this is the equation for maximum kinetic energy. I already explained that the charged particle will get the maximum kinetic energy when it reaches the periphery of the Ds. Okay, and the equation is half mv max square. V max is the maximum velocity and the velocity becomes maximum when it reaches the periphery of the Ds. So the equation is q square v square capital R square divided by 2m, where capital R is the radius of the Ds. Okay, and you can write the same equation in terms of the cyclotron frequency. So you will get the equation as 2 pi m nu square into r square. From the equation, you can see that the maximum kinetic energy is directly proportional to the square of the radius of the disc, and maximum kinetic energy is directly proportional to square of the frequency. Okay, so these are the important points about cyclotron. And one more important point, once again I am telling you that this acceleration of charged particle to very high energy is possible only when there is a resonance between the frequency of the cyclotron motion and the frequency of high frequency oscillator. When this resonance is lost, the charged particles are not further get accelerated. Okay. Next, you can expect questions from the limitations of cyclotron. One of the limitation is it cannot be used to accelerate neutron, because neutron has no charge. Cyclotron can be used to accelerate charged particles. Second point, that is limitation due to relativistic effect. We know that according to Einstein's theory of relativity, mass m is equal to m0 divided by root of 1 minus v square divided by c square. According to this relation, mass is not a constant when the velocity is comparable to the velocity of light. And when the velocity increases, the mass also increases. The time period t is equal to 2 pi m divided by qb increases, and the cyclotron frequency qb divided by 2 pi m decreases. So what happens when the particles reaches some higher velocity? It gets out of resonance because the cyclotron frequency is changed. Okay, so the charged particle will get out of resonance. I already told you the charged particle can be accelerated to very high energy when there is a resonance between the high frequency oscillator and cyclotron frequency. Since here the mass changes, frequency also changes, so it gets out of resonance, so we cannot further accelerate the charged particles. Okay, this defect is overcome in synchrotron by adjusting the magnetic field, and in the case of synchrocyclotron, this defect is adjusted by the frequency of the high frequency oscillator used in the cyclotron. So you can eliminate this limitation by using synchrotron or synchrocyclotron. Now we want to discuss about the path of a charged particle moving in both electric and magnetic field. The last session we studied about the motion of the charged particle in uniform magnetic field only, but here both fields are present. And I already told you that when you are solving the problems, you have to consider the force acting on the body. In the case of the particle moving a magnetic field only, you consider magnetic Lorentz force. But here both the fields are there, so you have to give importance to which force? That is called a Lorentz force, that we already studied. Now here the Lorentz force is F is equal to Fe plus Fm, that is equal to Q into E vector plus V cross B. This is the equation. Okay, and here we are analyzing this in different cases. So the first case is when the electric field, magnetic field and velocity are collinear. Okay, all are collinear vectors like this. This is electric field and the magnetic field also in the same direction, and the charged particle is also moving in the same direction. Okay, collinear. or it may be in the opposite direction. In this case, we can say magnetic Lorentz force is 0 because theta equal to 0. If they are opposite, theta is equal to 180. Okay, collinear means theta equal to 0 or 180. So here the magnetic Lorentz force acting on the particle is 0. But due to electric field, it experiences electrostatic force, and electrostatic force is equal to QE. So the total force is what? Only due to electrostatic field, and the total force is given by Q into E. So this is the net force acting on the charged particle in this case. Okay, since the force is there, you can find the acceleration. So what is the acceleration? Force divided by mass, that is QE divided by M. Now we can say the path of the charged particle. Okay, here the electric field is acting along the direction of motion of the charged particle. We can say that the particle is moving along a straight line. So the path of the charged particle is a straight line. But what type of motion? Here it has an acceleration. So it is an accelerated motion along a straight line. Or decelerated motion also. Why it is decelerated? If the electric field is opposite to the motion of the charged particle and the charged particle is positive. Okay, the charge is positive and electric field is in the same direction. So it has an acceleration. The charge is positive but the electric field is in the opposite direction. Then it has what? Deceleration. So you can say that it is a uniform motion along a straight line. So we can say it is a non-uniform motion. So we can say it is a non-uniform motion along a straight line. So it is no uniform motion along a straight line. You got it? Okay. And you can find the velocity of the particle after a time by using V is equal to U plus AT. And also you can find what is the displacement of the charged particle during a time interval t. S is equal to ut plus half at square. Like that you can solve the problem. Okay, so the basic idea is to calculate what is the net force acting on the charged particle. Okay, now the second case, electric field, magnetic field and velocity vector, all the three are mutually perpendicular to each other. Or you can say that when the charged particle is moving, crossed electric and magnetic field or transverse electric and magnetic field, what happens? Okay, what is the path? What are the force acting, like that? Questions you can expect. For example, you consider electric field is acting along positive y direction, magnetic field along positive z direction and velocity along positive x direction. Then what is the net force acting on the particle? We can say that F is equal to Q into E j cap plus V I cap cross B k cap. I cross k is minus j, so this equation is Q into E j cap plus VB into minus j cap. In both terms j cap is common. You can take it out. So the net force acting on the particle is given by F vector is equal to Q into E minus VB j cap. So this is the net force in this case. Okay, now let us consider a special case that we are adjusted the magnitude of electric field and magnetic field in such a way that the net force becomes 0. So if F equal to 0, what is the meaning? The meaning is this one, QE equal to qvb. That is, magnetic force and electrostatic force are equal, or you can say V equal to E by B. So this is a special condition for the net force equal to 0 when the charged particle is moving through a perpendicular electric and magnetic field. You got it? That is, charged particle should travel through a region containing both electric and magnetic field, and all these parameters E, V and B are mutually perpendicular. Okay. Then the net force is 0, or the charged particle will move undeflected, that is along a straight line, only when it satisfies this condition, that V equal to E by B. Okay, and this principle is used in a device called velocity selector. Velocity selector. So what is the principle for velocity selector? V equal to E by B. So remember this point, this is a very important question. You can expect this question like this. Electric field is there, magnetic field is there, and electric field and magnetic field are mutually perpendicular, and a charged particle is moving. That charged particle's velocity is perpendicular to both E and B, and it is traveling without any deflection. Then what is the speed of the particle? What is the answer? V equal to E by B. If electric field and magnetic field are given, you just find out the ratio, you will get the value of the speed of the particle. Okay, let us discuss the case 3. Here electric field and magnetic field are parallel. Charged particle is moving perpendicular to the electric field and also perpendicular to the magnetic field. Let me explain by using an example. Here electric field and magnetic field are acting along positive y direction, and charged particle is moving along positive x direction. So we can solve this problem by finding the net force. So what is the net force here? Net force is the Lorentz force. So substituting these values, we will get the force is equal to Q into E J cap plus V cross B. V cross B means velocity is I cap cross J cap, that is K cap. So it is equal to VB K cap. So this is the net force, and you can find its magnitude, that F is equal to root of Fx square plus Fy square plus Fx square, that we already studied. You can find the magnitude. Now my question, because of this electrostatic force, the charged particle get accelerated along y direction. So along y direction there is an acceleration, and the particle describe a straight line motion with a change in velocity. Okay, and because of the magnetic force, since the particle is moving perpendicular to the magnetic field, the particle should describe a circular path. So because of these two forces, the particle should describe an exact path called helical path. Okay, but what type of helical path? Helical path with a constant pitch or increasing pitch. We know that here this electric field increases the speed of the charged particle, so the particle will describe a helical path with increase in pitch. Okay, and which one is the axis of that pitch? Sorry, which one is the axis of that helical path? We know that we already studied this helical path. The axis of the helical path is the magnetic field, so axis is the magnetic field. So y-axis is acting as the axis of the helical path. Okay, and the path is like this. This is y-axis, magnetic field, and the same electric field, and this is x and this is z. So what is the case here? So the particle will describe a circular path, but its pitch is goes on increasing like this. So this type of helical path it will go. Not a radius, actually the pitch is increasing. Pitch is goes on increasing, but the radius remains the same. Okay, so this is about the case number 3, when the charged particle is moving perpendicular to electric field and perpendicular to magnetic field, but electric and magnetic field are parallel to each other. Okay, next fourth case. In this case, electric field and magnetic field are perpendicular, but the charged particle is released from rest. Okay, you can analyze by deriving the equation. We get an equation for cycloid. So you can say here the path followed by the charged particle is cycloid. So what type of path? Cycloid path. When the electric field and magnetic field are perpendicular and the charged particle is released from rest, then it will describe a cycloid path. You got it? And what is the net force acting here? The net force acting here, it is equal to Q into vector E plus V cross B. This is the equation. Okay, like this type of path you will get. Okay, so that's all about the motion. So we discussed the first session, and this session contains magnetic Lorentz force, motion of the charged particles in magnetic field, then through both electric and magnetic field, finally cyclotron. Okay, in the second session, in the next session, I wish to explain Biot-Savart law, its applications, Ampere's circuital theorem, and force acting on a current carrying conductor placed in magnetic field. Okay, thank you for watching this video.